Hello students. So this video will slightly help you to understand the basics of surface tension, capillarity, then one problem from Pascal's law and one from YouTube manometer where we'll be measuring the vacuum pressure. So surface tension, as we have already discussed about cohesion and adhesion, when you have a fluid, there will be two types of forces. One is a cohesive force, the other is an adhesive force. Yeah. One is a cohesive force and the other one is your adhesive force. So the cohesive force is the force between the like material, right? Maybe water molecules, they have the same attraction, right? So the surface tension due to cohesion between particles. So that is your cohesion, right? So they have the same liquid. When you have adhesion, it is between two unlike molecules. For example, water with glass, water with oil, because oil will not mix. So water and oil, those molecules will have a different force. So that is your adhesion. So cohesion is between the same material or same molecules, and adhesion is between different or unlike molecules. Now when you take water surface, now this is the free surface, so you have water throughout. So now this molecule, if you take this molecule A, it has throughout the 360-degree water molecule. So there will be a molecule here which will attract. There is a molecule here where there is a force here. Now the force on all the directions are equal as it is the same molecule throughout. The same in case of B. When you come to C and D, at this boundary, you have a air in contact. So the elements that are at this surface is being attracted by water, that is a liquid molecule. So they are cohesive force, same material. Whereas here you have adhesive force. So the force of cohesion and adhesion will be different. So due to this, there will be a net force that is acting. So again, the member for D again experience the same kind of force. Throughout this 180 degree, it will be experiencing cohesion, and at this surface along the line, that is the border, it experiences an adhesive force. Now due to this, there will be a slight tensile force, right? The stretching of member will take place. Due to this, there will be a slight tensile force which creates surface tension. And the formula for liquid jet is given by the formula. So for a liquid jet, it is 2 sigma by D. For soap bubble, it is 8 sigma by D. And for water droplet, it is 4 sigma by D, which the derivation has been completed. So this is for a water bubble, water droplet, where you have water throughout. This is for a soap bubble where you have both inside and outside you have surface tension, because inside you have air, it is an empty space, so you have air, then there is a thin layer of liquid, and then outside also you have air, so you have experiencing surface tension on both the side. So you have 8 sigma, that's why you have 2 into sigma into pi d. This is your surface tension that is acting throughout the perimeter. This is your excess pressure. This P that we are discussing here is your excess pressure, which again has been discussed. So your liquid jet, we have started with this, so 2 sigma by D. So you can keep this in order. First one is your liquid jet, which is given by the formula 2 sigma by D, which is your excess pressure. For droplet, it is given by the formula 4 sigma by D. And for your soap bubble, you'll have the formula as 8 sigma by D. So this way you can remember 2, 4, 8 and sigma by D is a constant. The left hand side is your excess pressure PE. With this we have already solved the problem. Now capillarity. Now due to this adhesion and cohesive forces, when a member comes in contact, what if the cohesion is lesser and the adhesion is higher? Let us assume that you have inserted a small tube inside water. Now the adhesive force is slightly higher than the cohesive force here, as noted here. So since the adhesive force is higher, the molecule, rather than being attracted towards the water molecule, it gets slightly risen up in the water tube, small tube. So the rise in this level, right, because as we have discussed, this pressure is equal to the pressure that you have here. So that is, if you increase the pressure outside, obviously the water will rise up. So that is due to the difference in pressure. But here we are not increasing the pressure, rather this is purely due to adhesive force. So there will be a slight rise. This will not be a very huge value. This will be a slight rise in, and that should be a small tube. The diameter will be very small. It is not going to be a very large tube. So since the diameter is also small, you will have a slight rise in water level. That is called as surface tension. Whereas in the case of mercury, your adhesion is less than cohesion in terms of glass. Right? We are taking it with respect to glass. So when the cohesion is higher than the adhesion, the water level will not even come to the same level as the outside. This is called as capillary fall. So you'll get your H is negative here. Your H will be negative. So you have a positive H and a negative H. If the H is positive, it is called as capillary rise. If the H is negative, then it is called as capillary fall. That is again determined by the angle of contact. For water with glass, it is 0 degree. For water with mercury, it will be around 130 to 140. We can also take 130 degree, which we have followed in the books. So you have it here. Yes. So this is your angle of contact. So we'll try to solve for a problem. Before that, we'll take the formula. So your final formula for capillarity, H is equal to 4 sigma cos theta by rho GD. When theta equal to 0, you can take this formula in case of water. But your generalized formula is the capillary rise or fall, capillarity, right, is given by the equation. H is equal to 4 sigma cos theta by rho GD. We are not going into the derivation. We'll just take the formula. So with this, we'll try to solve one problem. Now we have to take capillarity, calculate the capillary rise in a glass tube of 3 mm diameter. So the diameter is given. When immersed vertically in the sea, look at the value, it is 3 mm, very, very small. Vertically in case 1, water, and case 2, mercury. The surface tension for mercury and water is 0.52 Newton per meter and 0.0725 Newton per meter respectively, and the specific gravity of mercury is given, but make sure you remember this value. In case if it is not given, you have to remember. So let us try to solve for case 1. Now case 1, your diameter is 0.003 meter. I'm converting it in terms of meter. Keeping it in mm will also do, but let us try to have the habit of converting into SI unit and do it. So meter, then you have sigma is 0.0725 Newton per meter. This is in meter. You have to be careful when you convert it. Then the formula H is given by 4 sigma cos theta by rho GD. Now for water, theta equal to 0 degree and diameter is given. So sigma is given, sigma water. So you have density. Now density of water at normal condition is 1000 kg per meter cube. So substituting H is equal to 4 into 0.0725 into cos 0, which is 1, but eventually you can do it in your calculator. 1000 into 9.81 into 0.003. Now if you use this to calculate, you'll end up with a value, so which I have already done, and I'm not going to do it here, as you can do it with the help of your calculator. So the value, you'll get it around 0.98 centimeter, or you can write it as 9.8 meter. The actual value you'll get is 9.8 into 10 power minus 3 meter. Sorry, this is mm. So 9.8 into 10 power minus 3 meter. This is what you'll get. Now this is the answer for case 1, which is in case of it is water. Now for case 2, when you have mercury, theta is actually around 130. You have the surface tension is given as 0.52 Newton per meter. So your formula H is equal to 4 sigma cos theta by rho GD. Now the density of mercury is given by 13.6 into 1000. As specific gravity, S is equal to density of mercury by density of water. So taking it to the other side, I'm multiplying with 1000. So my H is equal to 4 into 0.52 into cos 130 divided by density is 13,600 into 9.81 into diameter, that is 0.003. So once you solve this, you will end up cos 130. Cos 130 is in the second quadrant, which is actually negative. So you'll have negative 10 power minus 3. Technically, we can cancel these two. and calculate this, this is what you will end up with, 5.8 centimeter, right? So that will be supposed to be mm, I think. So you'll get it around 5.8. So this is the value of your diameter. We are finding the minimum size of your tube. So this is the value for your capillarity in terms of we are finding the diameters when the value of h is given. So we'll go ahead with the next question. This is in terms of Pascal's law. So according to Pascal's law, the pressure that is acting on a fluid is constant throughout. So P1 is equal to P2. For example, you would have seen hydraulic ram. So I have a small opening here and a large opening here. This is A2, this is A1. So when I apply a force here, that is getting converted into pressure P1, force by area. That is being transferred here. The pressure here also same. So my F1 by A1 should be equal to my F2 by A2. So my F2 can be found from the formula F1 by A1 into A2. So since my A2 was larger than A1, this ratio is greater than 1. A2 by A1 is greater than 1. That technically means my F2 will be greater than F1. This is the application of Pascal's law of the hydraulic rams. So we will be trying to solve one question in that. Now we have the diameter of a small piston and a large piston of hydraulic jack-up, 3 centimeter and 10 centimeter respectively. A force of 80 Newton is applied on the small piston. Find the load lifted by the large piston when the pistons are at same level and the small piston is 40 centimeter above the large piston. So we'll take the first question first and then go ahead with the second question. So we have a ram. Now this is my large piston and this is my small piston. There is a force that is acting here which is being given out here as F2. This is F1. They are at the same level. So the pressure here and here are equal. So my pressure P1 is equal to P2. So my F1 by A1 is equal to F2 by A2. So my F2 is equal to F1 into A2 by A1, which is equal to, now my F1, that the force that I have applied is 80 Newton. My area for case 1 is, my A1 can be found using the formula pi by 4 into 3 square and my A2 can be found using the formula pi by 4 into 10 square. I am keeping it in centimeter. Anyway, since we are going to divide it, the 10 power minus 3 or 10 power minus 2 here, since it is from centimeter, that is not going to affect the value. So F1 is 80 into pi by 4. In case you want, you can do it. For example, 3 into, this is 10. A2 is 10 into 10 power minus 2 the whole square divided by pi by 4 into 3 into 10 power minus 2. I'm converting it into meter the whole square. So this and this I can cancel it out. That's why I didn't find the area directly, because anyway it is going to be cancelled out here. 80 into 100 into 10 power minus 2 the whole square divided by 9 into 10 power minus 2 the whole square. I'm using the law of exponents. So these two will cancel. So I'll get it as 80 into 100 divided by 9. So simplifying this, we will end up with the value as 888.9 Newton. So this is the output load you get. See, I have applied a load of 80 Newton, whereas I'm ending with the value of 889 Newton. So the force is being multiplied so large. So this is the case 1. So the case 2 that we have here is slightly different from case 1. Now the case 2 is like this. So this is my piston 2, which is the larger piston. My piston 1 is slightly at a height of 40 centimeter from piston 2. So this is 40 centimeter. So the pressure will be equal at the same level. So that technically means my total pressure now on the left hand side is P0 plus rho GH. We have just discussed this in the case of pressure. So P0 plus rho GH is your total pressure here at this point. Now this pressure is being transferred here. So at the same level. So the pressure will be equal at the same level. So whatever pressure I have here is being transferred here. So here I'm writing it as F2 into A2. Sorry, F2 by A2. So this is my pressure on the left hand side. Here I have written it here. So to find the total pressure at this point, my right hand side pressure, right, this pressure, right hand side pressure is given by P naught. Right, this P naught is the pressure that I create here. At this point, I have created a pressure forced by area. That pressure plus the height of this fluid will create a pressure. That is what is my rho GH. So P naught plus rho GH can be written as F1 by A1 plus rho. Since we are using water, it is 1000 into 9.81, that is the gravity, into height is 0.4. So if I substitute my F1, that is 80 Newton, divided by my area. Here maybe I require the area. So the area I have calculated as 7.068 into 10 power minus 4. That is pi by 4 into 3 into 10 power minus 2 the whole square. This is my area plus 1000 into 9.81 into 0.4. This when gets simplified will give you P rho GH plus P naught, that is my F1 by A1 plus rho GH can be 11.70 into 10 power 4 Newton per meter square. So this is the net pressure, right? Instead of having it as 11.31, this alone is 11.31 into 10 power 4. So now due to the water column for a height of 40 centimeter, I have it as 11.70. Now my F2 by A2 should be equal to 11.70 into 10 power 4. So my F2 is equal to 11.70 into 10 power 4 into the area 2. Again, if you calculate with the meter, 7.85 into 10 power minus 3. 5 by 4 into 10 into 10 power minus 2 the whole square. This will give me a value of 918.64 Newton. So there is a slight increase in pressure load, that is your output load, because of the water column's height. Because you have a column of 40 centimeters, this again adds a pressure to the system. So what we have here is a simple manometer, which is U-tube manometer containing mercury and is connected to a pipe in which you have an oil of specific gravity 0.8. The pressure in the pipe is vacuum. So this is very important because based on this only we will be drawing the diagram. The other end of the manometer is open to the atmosphere. We have to find the pressure in the pipe if the difference in the mercury level in the two limbs is 20. So if we draw the diagram, so since it is vacuum pressure, the level will be like this. So we have the metered fluid here whose pressure we are measuring, and there will be the manometric fluid which will be again here. It will be up to a certain level here. Since the pressure here is vacuum, the fluid will be trying to enter into this system, so the level will be below the pressure here. So this is our reference level AA. So this is your H2, this is H1, and this is your pressure PB. So PB is equal plus rho G H1, rho 1 G1 H1. The net pressure on the left hand side is equal to rho 2 G2 H2 is equal to the pressure on this is your right hand limb, which is your atmospheric pressure. For calculation, we'll take it as 0 as the gauge pressure. Now the difference in mercury level from both sides is 20 centimeters. So the level here, this is your mercury and this is your mercury level. So this is 20 centimeter, and the left limb, the height of the oil in the left limb is 15 centimeter below. So your H1 is 15 centimeter. So your pressure PB is equal to minus into rho 1, which is an oil of specific gravity 0.8. This is rho 1. So 800 density into gravity, which is 9.81, into H1, which is 0.15 meter, plus rho 2, which is specific gravity 13.6 or 13,600, into the gravity is 9.81, into the H2 value is 0.2 meter. So substituting this and simplifying, we will get the negative pressure in terms of Newton per meter square. If you want, you can convert it into Newton per centimeter square. So that's it. So that's the basic about your surface tension capillarity, problems in capillarity. Here's all problem in Pascal law and a simple U-tube manometer problem. We'll be going ahead with the differential U-tube manometer in the upcoming lectures. Thank you. Happy learning.